Angular momentum. As was done in the last chapter, we won't derive angular momentum from linear momentum. We're just going to substitute in the angular values for the linear ones. So linear momentum is lowercase p, and it's equal to mass times velocity. Angular momentum is capital L, and instead of mass, we put in moment of inertia. Instead of velocity, we put in angular velocity, omega. The conservation of linear momentum states that in the absence of external forces, momentum is conserved. This came from the original statement of Newton's second law. So this is how Newton originally wrote his second law. If there are no external forces, then some net force here equals 0. Therefore, the change in momentum is 0. There is no change in momentum if there are no external forces. Therefore, momentum is conserved. And we can use Newton's second law rotationally. Just like we had net force equals change in momentum over change in time. And by the way, momentum is mv over t, and v over t is a. So that's how you get F equals ma from that equation. So if you just plug in the rotational equivalence, instead of net force, we have net torque. Instead of change in momentum, we have change in angular momentum, and we still have change in time. But if there are no external torques, then net torque equals 0. Therefore, there's no change in angular momentum if there is no net torque. Angular momentum is conserved. The standard example used to illustrate the conservation of angular momentum is the ice skater. Start by assuming a frictionless surface. Ice is pretty close to that, although if it were totally frictionless, the skater wouldn't be able to stand up and skate. The skater starts with his arms stretched out and spins around in place. He then pulls in his arms. What happens to his rotational velocity after he pulls in his arms? After you discuss this in your groups, you can click on the link below and see if you were correct. Why did this happen? Just in case you didn't watch the video, when the ice skater pulls their arms in, they spin faster. Now let's figure out why that happens. Let's look at how her moment of inertia changes. So when the arms are outstretched, some of her mass is out here. Here's the axis of rotation, and we have mass that's very far away from the axis of rotation. Therefore, because moment of inertia is the sum of every piece of mass added together, the sum of mr squared for each piece of mass. If you have mass that's very far away from your axis of rotation, that's going to contribute to a greater moment of inertia. Here, once the arms go in, all of her mass is very close to the axis of rotation, therefore decreasing her moment of inertia. If we assume that the ice is frictionless and therefore is not applying any sort of external torque, angular momentum is conserved. Nothing's going to change it. So therefore, if L stays constant, over here, the angular momentum stays constant because there's nobody else around like pushing on her to change her speed or anything. There's no external forces. Therefore, if angular momentum is constant and your moment of inertia decreases, that means your angular velocity increases. She spins faster. So here, if angular momentum is conserved, the bigger your moment of inertia, the smaller your angular velocity, and vice versa. By assuming a nearly frictionless surface, that implies there's no net external torque, right? It equals 0. Therefore, conservation of angular momentum can be used. Delta L equals 0. Change in angular momentum is 0. There is none. Therefore, the initial angular momentum equals the final angular momentum. So what is angular momentum? I times omega. Therefore, initial conditions are going to equal the final conditions. You can solve this for, let's say, final angular velocity, and you can solve a problem based on the change of shape of the object, therefore the change in moment of inertia, and the initial velocity. Let's look at another example. In this case, a mass is hanging from one side of a spool of thread, providing a constant torque, an external torque, with no slipping. Since the torque is constant, the spool will spin faster and faster as the mass falls. First, let's calculate the tension in the string. Then, we will calculate the change in angular momentum over time span delta t. Step 1. Calculate the tension in the string. Let's say that down is positive. Let's say that's the direction of acceleration. I think it's easier to make whatever direction the system is accelerating positive. So down is positive and clockwise is positive. All right, you should know how to do this by now. This is just a review. We have two free body diagrams here, one for the spool, one for the mass. For the mass, we have linear motion, so we can just use F equals ma. The forces are mg minus t, because remember, down is positive, and the mass is m, and we have a. We can solve that for t. Over here, we also have one torque being exerted on the pulley. Yes, there is also gravity, the weight of the pulley, but the force of gravity is acting on the center of mass, not causing rotation, so we don't have to consider it. The only torque acting is the string over here. So the torque is the tension in the string, that's the force, times the distance that it acts from the axis of rotation, r. So that's our torque. Then we have the moment of inertia of the pulley, 2mr squared, and we're immediately going to replace alpha with a over r, because remember, when there's no slipping, a equals r alpha. Therefore, alpha equals a over r. Then we can cancel out those r's, and we can solve this for a. A equals t over 2m. Now let's combine these equations on the next slide. On the previous slide, we had t equals mg minus ma, but then from the rotational world, we had that a equals t over 2m. So we're combining those worlds, substituting in, and then we're just going to simplify. So this m cancels with that m. We get minus t over 2, 1/2 t. Then add that to the other side. 1t plus 1/2 t is 3/2 t equals mg. Therefore, tension is 2/3 mg. Now that we have the force, we can calculate the change in angular momentum. This equation is on the AP equation sheet. Change in angular momentum equals torque times time. So the torque is the force being exerted by the string times its distance r. This should be a capital R. But anyway, delta L equals torque, RF. And what is the force? We just found it, 2/3 mg times time. Therefore, that's our answer. That's going to be the change in angular momentum. It's directly proportional to the radius of the spool, the mass of the spool, and the hanging mass, which is also the same m, g, so it depends on the planet you're on, and the amount of time that the torque is applied. Let's consider the scenario below. You throw a dart at a bicycle wheel that's mounted on an axle. The axle's right here at the axis of rotation, and let's assume it's frictionless. Therefore, the wheel is free to spin, but it's not going to roll forward translationally. The dart sticks into the wheel and the wheel spins. If the system consists of the dart and the wheel, then there are no external torques. There are external forces, like for example, the axle is exerting an external force on the wheel, but it's not exerting a torque because that force is acting at the axis of rotation. So, a torque is RF sine theta, R would be 0. However, before the collision, the wheel's not rotating. Either is the dart, nothing's rotating. After the collision, the wheel is rotating. If angular momentum is conserved due to the fact that there's no external torques, and the wheel has angular momentum after the collision, where did the angular momentum come from? As it turns out, objects moving in straight lines do have angular momentum when in relation to other axes of rotation. By itself, the dart has no angular momentum. However, in the context of the wheel, it does have angular momentum. The angular momentum of an object moving in a straight line is RmV sine theta. Let's derive this equation on the next slide. All right, so as we know, angular momentum equals I omega and V equals R omega. Thus, we can solve this for omega. We'll make it V over R. If we then plug that in for omega here, we get L equals I V over R. We also know that I equals mr squared for a point mass. So we're going to say the dart is acting like a point mass. It's not rotating like an extended rigid body. So if we plug that in for I, we get mr squared V over R. Therefore, one of those r's cancels, and we end up with RmV sine theta. But where did that sine theta come from? It all comes down to the angles. As the dart approaches the wheel, the dart's velocity vector, shown here in green, makes an angle theta with the r vector, a line that connects the point of collision and the axis of rotation. It turns out the value of y, this line right here, the perpendicular component of this triangle, is the determining factor in calculating the dart's angular momentum. Therefore, to mathematically represent the length y, we can use the sine function. Sine theta is opposite over hypotenuse, that's y over r. Therefore, y, the component we care about, equals r sine theta. And that's where we get this r sine theta in the equation. Here's a classic problem about what we just learned. Below, we have a piece of wood connected to a table with a frictionless axle. We are looking down on the table, therefore this is an aerial view. So these are not like going to be projectiles where they're falling. We're looking down on a tabletop, like here's the tabletop. So these are moving horizontally on the table. We are going to slide two identical hockey pucks into the piece of wood and compare the resulting rotation of the piece of wood. Hockey pucks A and B have the same mass and initial velocity. Let's assume there's no friction on the table, or see the axle is also frictionless. Which collision will cause a greater final angular momentum of the piece of wood? And we're going to assume these collisions are taking place one at a time, not at the same time. Since hockey puck A collides with the piece of wood farther away from the axis of rotation, see how RA is greater than RB, the piece of wood will gain more angular momentum from that collision. See, V here is perpendicular to R, therefore sine 90 becomes 1, and therefore this equation becomes the angular momentum of the hockey puck is RmV. The greater the distance of the collision from the axis of rotation, so if you increase R, this distance here, the greater the angular momentum of the hockey puck. Angular momentum of the hockey puck, so the angular momentum of an object moving in a straight line, is directly proportional to R, M, and V. In this example, we have two different objects, a piece of clay and a hockey puck. Both objects have the same mass. We're going to say it's m over 3. They each hit the piece of wood with mass m at the same location, a distance r from the axle, and they have the same initial velocity. However, the piece of clay is going to stick to the piece of wood and rotate with it, while the hockey puck is going to bounce straight back with the same speed that it had, but in the opposite direction. In which case will the piece of wood have the greatest final angular velocity? And here we are given that this object, with an axle here at the bottom, has a moment of inertia of 1/3 mr squared. All right, let's start with the clay. The system includes the clay and the wood with no external torques. The axle at the bottom is exerting an external force, but it's acting at the axis of rotation, so it doesn't exert a torque. Therefore, angular momentum is conserved in both cases with the clay and the puck. Let's start with the clay. So we know angular momentum is conserved, therefore L initial equals L final. Initially, the only thing moving is the clay. So initially, we only have the angular momentum of the clay. Then it sticks to the wood, and then they rotate together. Therefore, at the end, together, they are now one object with angular momentum. As we discussed previously, an object moving in a straight line has angular momentum of rmv sine theta, but because this is a perpendicular angle, that sine theta goes away. Now, r is the distance, capital R. The mass of the clay is m over 3, and the initial velocity we're calling v naught. Over here, we now have a rotating object that has angular momentum. Since it's a rotating object, we just use I omega. All right, so we keep the left side of the equation the same. A tricky thing here is that the wood with the clay stuck to it now has a new moment of inertia, right? The moment of inertia has changed. You have to add the mass of the clay to the overall moment of inertia. So we have 1/3 mr squared, which was the original moment of inertia, but then we're adding this mass. So remember, to add a piece of mass to the moment of inertia, you just add mr squared. So the mass of that clay is m over 3. Its distance of the collision distance is r squared, omega. Solve this for omega, we get v naught over 2r. All right, now we have the hockey puck. The hockey puck is going to collide and then bounce back with a velocity of negative v naught. So initially, the only thing moving is the puck. After, the puck now has negative momentum, so we'll have the final momentum of the puck, and the wooden rod also has angular momentum. So now we have two objects with angular momentum. Just like before, the angular momentum of the incoming object is r m over 3 v naught, because that's r m v sine theta. That is the angular momentum of an object moving in a straight line. And everything about it is the same. Same distance, same mass, same initial velocity. However, after the collision, it now has negative momentum, right? If to the right is positive, that means to the left is negative. So we have the same momentum, but in the opposite direction, hence the negative sign. And the rod has angular momentum as well, I omega. All right, so this one gets added to the other side, and now we have two of them. 2 times this. The moment of inertia of the rod is 1/3 mr squared, and it doesn't change because no clay is sticking to it. And we have omega. Solve for omega, we get 2 v naught over r. The clay sticks to the piece of wood. The wood ends up rotating with the angular velocity v naught over 2r, whereas the hockey puck bounces off with the same velocity. The wood has a final angular velocity of 2 v naught over r. The puck gives the wood 4 times the final angular velocity than the clay does.